Welcome to geothermal project. Through the 1960s, geothermal plant was being constructed worldwide. In United States installed more geothermal capacity. The traditional geothermal system are two wells are drilled into reservoir. The producer well pumps hot formation water to feed the power generating plant. The injector well returns cool water to the reservoir. Depending on the products from the reservoir surface, there are three common types of system: dry steam, flash steam, and binary cycle system. Canadian company Ever Technology has drilled a pilot for Ever Loop system, and it is not required water flows through reservoir. And this technology could be the future of geothermal technology. The financial cost of generating power from geothermal is between $100 to $600 per megawatt hour. Using the United States as a comparison, the upfront cost of geothermal energy usually around $10,000 to $20,000 USD. Next, Jimmy gonna talk about the objective of this project.
This brings us to the quantitative part of the project, where we predict true formation temperatures at given depths to determine whether old oil and gas wells can be repurposed for their geothermal energy potential. Our analysis is comprised of 4 steps. We apply EDA to explore data, determine what variables relate to formation temperature, find the right model to make predictions, and finally provide an economic case study at the end. The dataset we were given has 2 areas of interest: Alberta Duvernay and Texas Eagle-Eye. We were provided with a series of datasets that we then analyzed in detail. Initial EDA started with an overall look at the data. The true temperatures provided generally align well with research publications we found online. Then we performed some unsupervised clustering to evaluate common groupings that help drive further analysis. Most of our feature engineering is in the form of mapping, where we apply several different techniques, ranging from kriging, Gaussian, to neural network-based methods. We apply this to each and every variable we can engineer from well-log LAS files provided. Our modeling workflow is a progression of complexity. We start with simple linear regression to evaluate obvious relationships and trends. Then we leverage a tree-based model to perform recursive feature selection. Afterwards, we feed these learnings into a neural network model to improve model precision and accuracy. And finally, we perform boosting on the model results using cross-validation and various other techniques to help prevent overfitting. Now that takes us to the next step, which is the thermal energy potential calculation.
Hello everyone, I'm going to demonstrate how to calculate the thermal energy potentials. The equation is pretty simple. We have the mass flow rate, the heat capacity of water. We inject the water back to the ground when it cools down to 30 degrees. The challenging part is to get the temperature of the produced water at the wellhead. We already predicted the reservoir temperature at these 2 locations. With this flow rate, we need to then calculate the produced water at the wellhead. As we know, there are heat losses along the way the water is flowing up. The heat loss can be described using these 2 equations. We can then simulate the water temperature at different depths with different flow rate. Based on our extrapolation, we can then estimate the water temperature for these 2 locations. Assuming this is our use case scenario, with this equation, we can then calculate the thermal energy potentials.
Geothermal power plants do not burn fuel to generate electricity. Moreover, they emit 97% less acid rain-causing sulfur compounds and about 99% less CO2 than fossil fuel power plants of similar size. Most geothermal power plants inject the geothermal steam and water that they use back into the earth. This recycling helps to renew the geothermal resource and to reduce emissions from the geothermal power plants. Now let's move on to the business use case.
We can utilize geothermal energy in lots of different areas. We assess the 3 potential use cases this time. Our first use case is electricity generation. Geothermal generation is an energy source that runs 24/7 regardless of the weather. This is very applicable in Texas, especially during the weather-related power outage in winter 2021. Additionally, geothermal energy is a resource that can be ramped up and down to meet changing demands in real time. Our second use case is direct heat use. Alberta is a cold province and can benefit by using geothermal energy to heat homes and greenhouses. The last use case is to use geothermal projects to repurpose inactive wells in Alberta and reduce the unemployment rate. We did a comparison of electricity markets in Alberta and Texas. Their interconnected electric systems are ISO and ERCOT. They both operate at an energy-only market. Hence, power prices tend to be low but more volatile. They both have policies to promote additional renewable energy capacity. The differences between ASO and ERCOT are ASO has price cap at 1,000 and ERCOT's price cap is 9,000. In 2020, Texas' average pool price for residential customers is higher, and ERCOT's DC ties makes it more isolated from other grids. In conclusion, in terms of investment opportunities in electricity generation, both Alberta's and Texas' energy policy favors building geothermal electricity generation. Alberta has cheaper capital costs. However, Texas has bigger grid size, higher electricity prices, and greater need for a stable electricity source, which can potentially increase the returns on investment.
With that, we present two potential business propositions on oil and gas well repurposing based on the differences between Alberta and Texas. As was mentioned previously, the Texas electrical market is favorable, and a simple economic analysis shows that formation temperatures exceeding 200 Celsius could supply a power plant right at the wellhead. The project is estimated to break even in 10 years based on our assumptions. In Alberta, the electricity market is less favorable, but the alternative is agricultural heating, and specifically in this case, aquaponics, which is the better choice due to its higher profitability. We use a 1-acre area as our case study, showing a break-even estimate at year 9. Speaking to what we could have done differently, the most important aspect is our team being entirely comprised of non-domain members. With the addition of subject matter experts such as geologists or geophysicists, we could definitely have built a much better model. In conclusion, we believe we have completed the objectives of this project of predicting formation temperatures with well data and presenting potentially viable business opportunities for leveraging geothermal energy in both Alberta and Texas. Here are some of our references, and thank you for watching our presentation.